How's everybody doing today? Hope everybody is doing well. Let's go ahead and get started. Let me see. Okay. So today we are going to. How's everybody doing today? Well, hope everybody is doing well. Let's go ahead and get started. Okay, sorry about that. Okay, I think we're good. Sorry for that. I forgot to turn off the YouTube streaming and it was playing in the background. But let's get started now. I think everything is okay. I was gonna say, so we had been doing a combination of like entering questions in the chat on Zoom and also in the Slack. It's probably a little easier for me to monitor just questions in Zoom while giving the lecture. So maybe I would encourage you to put your questions in Zoom chat, even though we had said the opposite before. And then also I'll have, you know, any TAs who are there, and Alex can interrupt me with questions that they see in Slack if they like. That's great. Okay, so today we are going to be discussing descriptive statistics. So we're going to have sort of a quick and dirty introduction to statistics. We're going to be talking about a lot of different topics, variable types, how to compute descriptive statistics in Python, like the mean and the standard deviation, and a few other things, how to do some simple plots, the difference between correlation and causation, confounding variables, descriptive versus statistics, discrete and continuous random variables. So we do kind of have a lot of content to get through today. So let's dive in. So first of all, when we're dealing with data sets often consist of a collection of people or or objects with a bunch of characteristics or variables. And those variables are usually of two types, either categorical, which records a category. So that would be anything like gender, color, true, false, educational level, Likert scales, or a quantitative variable, which records a numerical measurement. And so a categorical variable, it might or it might not have an order associated with the categories. And in this lecture, we'll focus on variables, and quantitative variables can be of two types, either discrete or continuous. So discrete variables, you know, how to think of discrete versus continuous, hopefully you're a little bit familiar with the concept of discrete, but examples of that would be year born or counts. On the other hand, continuous variables are variables whose values are real, which can be essentially have an infinite decimal expansion. If you had a method of measurement that was accurate enough, you could sort of, you know, get an arbitrarily long decimal expansion. So examples of that would be length, temperature, time, where you don't have specific discrete values. Okay, so maybe just to go over a few examples. So for example, let's think about latitude. Anyone have a guess on that? Let me pull up the chat here so I can see. Oh, I think somebody has already answered the first little question here. So let's see how this goes. So latitude, quantitative continuous, yes, that's right. Olympic 50-meter race times, also quantitative continuous. Good. Olympic floor gymnastics score, quantitative discrete. Okay, well, maybe we'll discuss that one. Do we have any other opinions on item number 3? Quantitative discrete, quantitative continuous, or categorical? Definitely qualitative. Yeah, so it's actually, yeah, it's actually qualitative. It's a categorical variable. It seems quantitative because it's a number, but really it's a category. You know, you have a judge who's, you know, assigning their opinion, and they write it down as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but it's not really a numerical measurement. So that is actually a category. That one's a little tricky. College major, categorical. Number of offspring of a rat, quantitative discrete. That's right, because it has to be an integer, so that's discrete. Of course, rats have a lot of offspring, so there are some discrete variables that have so many different values that we kind of treat them as if they were continuous. And so you may run into that in the process of doing data analysis. Okay, so what's the point in sort of going over this? The main point is just that in statistics, we have one set of tools for quantitative variables, and we have another set of tools for categorical variables. What's helpful just to have this distinguishment in our heads as we do our toolkit in statistics. Okay, so first of all, in this lecture, we're primarily going to focus on descriptive statistics for quantitative variables. So we'll primarily be focusing on quantitative in just descriptive statistics and plots and all that, mainly for quantitative variables, which are nice because they consist of numbers. And when a variable consists of numerical values, we can do things like add the values together, take the average. Those are things that we can't do for a categorical variable. Okay, so our goal here is basically to describe a data set with a small number of relevant statistics or figures. So suppose we're given a sample of size n, and x1, x2 through xn are the n numerical values to sample. So some descriptive statistics we're interested in are the min, the max, the median, and the mean. I think you guys have seen all of those before. The mean you just compute by adding up all of the values in the data set and dividing by the total number of values. And Python, of course, has lots of functions and packages for computing statistics. And we'll use the Python package NumPy for a lot of these descriptive statistics. So first of all, to get started, I may need to zoom out a little bit more so I can get up. Oh, there we go. So here. So let me go ahead and run this. So what I'm going to do is I'm going to import the NumPy package as NP. So I'm just going to give it a little shorthand here so I don't have to type long words every time I want to reference it, and import pandas as PD. And then one other package that we'll be using today is matplotlib.pyplot. So that's for making lots of pretty pictures, and we're going to import that as PLT. And when you're importing this matplotlib, you may also want to include this line, which tells you that so that the graphs will be included in the notebook. Okay, and then there's lots of figure parameters that you can set. So there are defaults that come when you import this package, but you can also change the defaults. And so here we're going to specify the figure size that we want to be 10:6, and we'll use this plot style called ggplot, which adjusts the defaults a little bit. Okay. All right, so let's try this on an example. So let's say we're looking at the monthly average snowfall in Alta, October through April, and we'll compute some descriptive statistics of a small data set of these values. So this is snowfall data collected from 1980 to 2014. And if you're curious, you can check out, the source, but we don't, mainly we're just sort of getting used to the how to work with it in Python. So we can start off making a list out of these values. So we can first make a list. This is floats, discussed last time, of the snowfall values. And then we can also make another list, which is a list of strings, which contains the corresponding months for those snowfalls. Okay, and then if you ask Python what type the first list is and what type the second list is, it'll just tell you list, right? So the type for the first list is list, the type for the second list is list. It's not telling you a list of what. If you want to know the type of the elements of the list, you can ask more specifically, print the type of Alta average monthly snow first value. And so when you do that, you can see, okay, yes, the first list has floats. And if I do that for the second list, you can see the second list consists of strings. And you can use the len function to return the length of the vector. Okay, so now what can we do with some of the NumPy functions? Well, one you may be interested in is finding the min snowfall. So you can do, np.min Alta average month snow. You can also find the max of that vector. And so we see the minimum snowfall, 28.5, maximum snowfall, 99.66. And you may also be interested in not just what the maximal and minimal snowfall for those values were, but what month they occurred in. And so this argmin function.
Oh, I know.
So I got a little feedback there. Somebody trying to say something?
Yeah, I took care of it.
Oh, okay, thank you, Alex. I don't know, maybe somebody forgot to mute themselves. Okay, so the argmin command will tell you the index corresponding to the minimum. You can actually recover the month corresponding to. So then if you print imin, you can see, okay, that's corresponds to the first index, 0 index. And if I evaluate the months vector on imin, I can see that that's October. That's when the minimal snowfall occurred. And I can do the same thing for the max. I can use the argmax to recover the index of the maximal snowfall, and then evaluate the months at that index to see that that was in March. Okay, so that's just some little useful commands if you're manipulating data in Python. You can also calculate the mean. We get a mean of 80.4, and also you can calculate the median, which comes to 90.85. And just a reminder, the median is just the middle value in a data set. So if you have an odd number of elements, it'll be the middle value. If you have an even number of elements, you'll get 2 values in the middle, and then you would take the average of those 2 middle values to give you the median. And both the mean and the median are measures of what's a typical value for the data set. And there's sort of pros and cons to each as a statistic for the measure of center. Okay, so now that we've warmed up with some basic commands, let's look at how we would make some plots. So when we're doing exploratory data analysis, it can be really useful to visualize the data. So we're going to use the matplotlib to make several simple plots. Okay, so what I think I'm going to do here is to start off commenting all this out so we can kind of add one line at a time, and you can see how it adjusts the picture. You want to, this plot.show just tells Python to display all previous plots in one figure. So I'll just leave that set. But if I start off running this, oh no, what did I do? I think I forgot to actually import the packages up here. Let me see if that's what happened. I forgot to run things as I was getting so, yeah, that's fine, that's fine. Okay, let's try this. Okay, there we go. So, so this sort of the most basic plot you can make is with plot. And in general, that plots X versus Y. So if you have two variables, X and Y, that you want to plot against each other, you would do plot XY. You'll notice here, we don't have an X vector. This was just a vector of Y values. So what is Python doing here? It just defaults to plotting it versus an X of indices 0 through n-1. So it's just plotting this using the index as the x-axis and then using the vector of values as the y-axis. So that's kind of the default behaviors. So you can see that the x values it's using here actually correspond to this vector that you could also generate using the arrange function. If you did arrange 7, so you get the vectors 0, 1, 2 through 6, which is what's being used as the x values here. And you can add, if you want to replace those index values with the actual labels from the months vector, you can do that with this xticks command. So it'll just replace those tick marks with these strings from the months vector. Now we have nice labels on the x-axis. And if we want to see where the mean falls, we can do that here. Oh, I didn't think I was going to need the mean, but maybe I do. Let me just run the whole thing from the oh, sure, I'll do that. Make sure I didn't miss it. Okay, let me go back to where I was. Okay, so what this did was it made a line plot basically out of just 2 points. So we have 2 points, which is 0 and the mean snowfall, and 6 and the mean snowfall. And it's just going to connect those with the line because that's the default behavior of the plotting. And we could do the same for, oh, I think I got some questions and I didn't see them. Okay, let me kind of go back here. Well, what's the difference between range 7 and NP dot arrange 7? Good question. I think they're the same.
One is for
Alex,
NumPy, the other one is for just vanilla Python.
but they essentially behave the same way, right?
Exactly.
In terms of the indexing and the inputs and all that. Yeah, so I think you pretty much use them in the same way, but the arrange is specifically from the NumPy package. Okay, and we got another comment. There's also np.linspace, and that can be helpful if you want to automatically generate arrays like that. Okay, let me see. Let me see what other questions I got. I think that the plt.legend, that what is the label? I think that is the plt.legend that is commented out. Yeah, so let me keep, I just wanted to keep adding things one by one so you can see how they appear, right? So I can add the median, and then I can add the title with this title command. And then, yeah, the label is not used yet, but it will be if I tell it to make legend. So the X label is the label for the X-axis, month, add the label for the Y-axis, snowfall, and then I can add a legend. And right, you'll see once I specify to add the legend, it's going to draw the little legend with the labels that I specified earlier when I was making those plots. So now we have a nice picture. Okay. right, so now let's look at a slightly larger data set. So that was a really small data set where we could see all of the values. But now we're going to look at a SECUM data set from 1994. And I think I already ran this, so I don't have to run it again, but let me do this. So you can just, I'm going to import the data with this pandas read table command. And then I'll print if I print this type, you'll see that what I have is a pandas data frame, and what it looks like, you can see what it looks like by printing data or printing the head of data, and it'll just give you a snapshot of this data frame. Sort of what you see in this first column is just the index corresponding to the different rows in the data frame, and then we have these different variables. Age, employer type, not sure what that one is, education, marital status, occupation, etc. And it'll also, it shows you the first few rows in the data, and it shows you the last few rows in the data. So this, you can see this data set is about 32,000, has about 32,000 entries. Okay, yeah. Okay, if we actually want.
Sorry, just the read panda data set, does that work for any data set, like SQL tables or any tables, or like specific types of tables does it need for?
Oh, for the read
yeah.
table, like what data frames does it work for?
Yeah.
I mean, like what type? Yeah, I think it's supposed to cover a broad range, but I haven't actually done it myself, you know, with a lot of different data types. I know there's also, like, if you have your data stored in a CSV file, there's a read CSV command. So that's also an easy way to import. But I think it is supposed to work with a broad range of data types, but you would probably have to adjust, you know, the syntax accordingly. Okay. If anyone wants to add something along those lines, feel free.
I'll just say we'll cover this in some detail, and there is plenty of different importers for pandas. Okay,
great, thanks. Yeah, so we have that to look forward to in our data frames lecture. Okay, so if you actually want to do some numerical analysis, then it's often helpful to make a list, you know, just your plain Python list out of one of the columns in the data frame. So I can do that. I can define this new list called ages, which is just my data frame evaluated on the age variable and exported to a list. Okay, so I define this in this way, and then I can print it, and I see now I just have all of the ages stored in a nice long list. Okay, so now I'm ready to do all kinds of descriptive statistics there. So I can compute the min, the max, the mean, the median. And so what do I see? That I see that the minimum age is 17, the maximum age is 90, and the mean and the median are actually quite close for this data set, 38.5 and 37. Okay, so let's see. Hold on 1 second. Here we go. Here I get my run button back. Okay. Okay, so this is helpful. We get some idea about the distribution of the data from some of those summary statistics, but we don't get a good sense of the shape. The fact that the mean and the median are close might indicate that probably we don't have a super skewed distribution, but it's hard to say without seeing a plot. So one of the main plots we like to look at is called a histogram, and that really shows you the shape of the distribution. So if we want to make a histogram of these age values, so let's do that. Again, I think I'm going to, well, I guess it won't comment that out. I'll just run this. And you can see if I use the hist command, the plt.hist, I'm going to make a histogram of ages. And here I'm explicitly defining the bends that I want to use for my histogram. If I wanted, I could just say use 20 bends and not specify what they are, and then Python will come up with a reasonable 20 bends to use. And I could even leave that command out entirely, and it'll default to using 10 bends. Okay, but you have more control if you want. You can specify exactly what you want the bends to be. But what does a histogram do? So it makes a collection of bends along the x-axis, and then it counts how many observations of the data set fall in the range of values of that bend. So here it looks like well, I'm not sure what the ranges they're using here, but something like 17 to 25. And then I've got like 5,000 plus people in that range of values. Okay, well, let me see. I've gotten some more. Let's see. Okay, I got another. I think I had another question that somebody already answered. How do you install packages through Jupyter? Yeah, okay, I probably won't discuss that right now. Maybe we can talk about that afterwards if there's still confusion. And what does the set equals comma mean? It was listed after the data set was read in. Let me go back up here. Yeah, I believe that that refers to the fact that the data set was a comma separated file. And so it's telling it how to read it in, that the file is comma separated. Someone might want to look that up to double check, but I believe that's what it's doing. Okay, and then okay, yes, good. All right, I think we touched on the important stuff. So let me keep going here. All right, so we talked about making histograms. So quantiles are also another important descriptive statistic. Quantiles are specific percentiles, and so they describe what percentage of the observations in a sample have a smaller value. So for example, if I run this here, what do I get? The 25th percentile of ages is 28. The 75th percentile is 48. And so that tells me that 25% of people are younger than 28. The middle 50% of people have ages between 28 and 48. And then the top 25% of the population is over 48 years old. Okay, and if I looked at this range, 28 to 48 is referred to as the interquartile range, and it's where that middle bulk of the majority of the data sits. And so how do I read off quantile histogram? So there's a sort of very straightforward relationship between reading off quantiles and area. So if I want to compute the 50th percentile in the data, that also corresponds to the median. I find the value that cuts the area of the histogram in half, and then I read off the bottom number. Or if I wanted to, estimate the 75th percentile, I would look for, well, where do I cut off a quarter of the area? And that's kind of maybe somewhere around here. That corresponds to the 75th percentile. So that's basically some basic statistics, how to do some basic plots. Another really important descriptive statistic other than mean and median is variance and standard deviation. So mean and median get at what's a typical central value data set, but in general, we're very interested in how much variation there is. You know, how consistent are the values and how much do they fluctuate? So there's one way of measuring this. Well, the interquartile range is one way of measuring that. Another way of measuring that is with the variance and standard deviation. So how do you compute the variance? You have to compute the mean of the data. So that's mu, that's just the average. And then you can compute the variance by looking at the average squared deviation of a point from the mean. So this is another average, but not an average of data values, an average of the distance squared from the mean. And then you take the square root of the variance to get the standard deviation. Nice thing about that is that the standard deviation then has the same units as your original data. If you're measuring things in feet, the standard deviation is also in feet. So it has a very natural interpretation in terms of the units. Okay, so with the NumPy commands, we can do .var and .std, and that'll give us the variance and the standard deviation. Okay, and so just to kind of visualize what the standard deviation means in terms of the shape of the distribution, this is like a little bell curve, which corresponds to a normal distribution. If the standard deviation is small, you're going to get a tall cell. You're going to have the bulk of the values really close to the mean. If the standard deviation is large, you're going to get this sort of fat, wide bell where you have a lot of dispersion. So you have a lot of observations that are far away from the mean. That gives you a large standard deviation. Okay. And another thing that we're very interested in when we're analyzing a data set is the relationship between variables. That's actually really useful. For example, if we have a ton of variables that we would like to build a model with just a few variables, well, maybe we can get a lot of variables if they're highly correlated with other variables. So one basic way that we can try to determine if there's a strong relationship between two variables is to compute the correlation coefficient between them, which is defined in terms of the covariance. So the covariance of two variables, x and y, is defined with the following formula. It's once again a mean, but it's the average of xi minus mu x times yi minus mu y. This will depend on the units that you're using to measure x and y. So we don't really look at that directly as often, but we define the correlation coefficient by taking the covariance and dividing by the standard deviation of x times the standard deviation of y. This now gives us a unitless quantity that's always in between -1 and 1. And if it has a large magnitude, either close to 1 or close to -1, it means there's a strong linear relationship between the variables. If it's small, if it's close to 0, it means there's not much of a linear relationship between the variables. So just to kind of show you some pictures, here are plots of x versus y for various choices of x and y, and the correlation is written there at the top. So you can see here I have perfect positive linear correlation, right? If the correlation coefficient, sometimes it's called R. So if R is positive, they're positively correlated. If R is negative, they're negatively correlated. And then when R is close to 0, when you plot them, you'll just see a big blob, right? You won't see really any pattern. You don't get any predictive power. One variable, you can't predict the other one. But one thing to be careful about is that the correlation coefficient only gets at whether there's a linear relationship. And so it could be that your variables do have a very strong relationship with each other, but it's not linear. So for example, if you pattern down here, if you got this in your scatter plot of X and Y, if you computed the correlation coefficient, you would get 0. But there's clearly a very strong relationship between these variables. You know, if you were to know the X value, you could say a lot about the Y value. It's careful to not assume that a low value of the correlation coefficient means there's no relationship between variables. It's just not as straightforward of a relationship. It's not linear. Or maybe there is none at all. That could also be. Okay, so let's see. So let's compute the correlation coefficient between age and hours worked per week. So we can make another list, which consists of the hours worked per week. And then I can do a 2D histogram if I want to kind of visualize this in 2 dimensions. And then I can compute down here the correlation coefficient between these 2 variables. And I can see, so this is just telling me the correlation of a variable with itself, which is always 1. So when you run this, you always get 1s along the diagonal. But what you're interested in looking at here is this value off of the diagonal, which is about 0.07. That's very low. So that's very low for a correlation coefficient. So we would say, yeah, there's not a strong linear relationship between these variables. Okay, and then is there a way to calculate higher dimension linear correlation? So do you mean, can I put in more variables here? Is that what you mean? Like I have 3 variables and I get like a 3x3 matrix instead of a 2x2 matrix?
If they don't seem to be correlated in 2D linear, then they may be correlated in a higher dimension.
Oh, so do you mean that
your visualization involves zero correlation? They're clearly correlated, but not in that 2D. Maybe there's a higher dimension that they're correlated in.
Yeah, it would be useful to actually plot here. Let me do another plot here, which is just our basic plot of ages, hours, and let me make a little, I think this is how I can make a little scatter plot. And so this maybe is more helpful. I don't know. To me, maybe this is a little bit more of a helpful plot. If I make a scatter plot of X versus Y, or in this case, age versus hours per week, you know, I just kind of see this blob. So in looking at it this way, I can see that there's not much predictive power that I have in knowing one of the variables to predict the other. So you can see that they're just kind of scattered pretty far here.
Based on that picture,
Okay.
If you assume there's a function that is correlated in there, maybe that function is just a projection onto 2D from a higher dimension. Does that make sense?
I don't think I follow the question.
So these points looks like they could fit on kind of a curve function. And that curve function could be just a projection, a higher dimension projected onto 2D. So it looks curved in 2D, but it's actually linear in a higher dimension. Does that make sense?
Well, these are one-dimensional variables. So I guess I'm not sure what you mean exactly about but is a projection from higher dimensions. But yeah, but maybe we could discuss that that more after class. Okay, so yeah, I mean, here we're just talking about looking at the correlation between, you know, between these one-dimensional variables. All right, so one other thing that's kind of important to be aware of when you're talking about correlation, and this is what you always cover in a very basic, well, what you cover in your first statistics course, is they'll drill into you that correlation does not imply causation. So just because two variables are strongly correlated, it does not mean one is causing the other. So here's a little graphic along those lines. I used to think correlation implied causation. Then I took a statistics class. Now I don't. Sounds like the class helped. Well, maybe. So I don't know. But anyway, it's kind of cute. But there's lots of examples of variables that have a really strong correlation with each other that you can automatically sort of tell that the relationship could not be causal. So here, for example, you have per capita cheese consumption is one of your variables, and then the other variable is the number of people who died by becoming entangled in their bed sheets. And these variables look really strongly correlated with each other, and they are, but there's no causal relationship between per capita cheese consumption and becoming tangled in your bed sheets, at least not one that I'm aware of. Okay, and if you want, you can check out this website. There's lots of other funny examples there too. Here's the revenue generated by arcades versus computer science doctorates awarded in the US. Okay, so.
Okay.
Sorry,
I think we have another question in the chat, but
Yeah,
I think
go ahead.
Alex answered it.
Oh, the question was answered?
Yes.
Okay, all right, good. Then I will keep going, but thank you for the heads up. Okay, so in the interest of time, I'm gonna skip this. Why don't we now, since it's 1:10, I thought I would change it up today and have you guys do the breakout rooms in the middle of the lecture to sort of, I don't know, have a break from me talking. So why don't we do the breakout rooms for 10 minutes until 1. Well, maybe we should do our bio break first. Let's go ahead and do that since we've been going in now without a break. Let's take a 5 minutes bio break. We'll come back at 1:15 and then we can go into the breakout rooms. Okay, so I'll see you back at 1:15.
Can I ask a quick question? Just
yeah, you may.
I was just curious. This NumPy function that gives the correlation coefficient between two lists. How do we interpret the result? It gives back an array with 4 different values.
Yeah. So this number right here that you read off, this is going to be the correlation coefficient between ages and hours. So this is correlation between ages and ages. This is correlation between hours and hours. And of course, if you take the correlation of a variable with itself, it just gives you 1. It's perfect.
Right.
But this is the correlation coefficient between ages and hours. So kind of in this case, you're just interested in reading this this off diagonal value.
Right.
So this number here, yeah.
So what's the purpose then of returning like these 4 separate values if it's, well, I guess, is it always going to be symmetric?
It's always going to be symmetric, yes. And I think the purpose of that is sometimes you might want to put in, like, throw in 10 variables. You want to explore all of the correlations between the 10 variables. And so in that case,
Oh, I see. It makes like a
want like
table.
that whole big matrix where, yeah, I don't care about the diagonal, but you want to look, oh, maybe 1 and 8 are highly correlated, maybe 2 and 7 are highly correlated, and you can just kind of look for the big numbers in a matrix. So it makes more sense if you're throwing in, you know, like 10 variables or 100 variables with 2 variables, not so much.
Okay, that makes a lot more sense. Thank you.
Yeah, no problem. I'm happy to answer any other questions while we're on break if anybody has them.
So if you want to look at specific ages and hours, would it be better to look at a confusion matrix?
So what do you mean if you want to look at specific ages and hours?
Like, I guess my question doesn't make sense.
Yeah, I mean, I think of a confusion matrix as something of is like in prediction when you have you know, different predictions associated with different data points, and then you look at like this confusion matrix of how they're related. But
Right. Yeah. Sorry, I just forgot
but
what the matrix was.
yeah, that's okay. I think maybe we'll get to that later in class. Maybe.
I just want to say I appreciate your use of all the KCD comics.
Oh, oh, I'm glad somebody's enjoying them.
Did you see him when he spoke at the O?
No, I didn't. I mean, I'm new, so I don't
Oh
know.
yeah,
When did
he came last year, just like a few months before the pandemic, actually. And
okay, so I missed it.
The book
Fun.
and he's such a good speaker.
Yeah, that sounds like a lot of fun.
Hey, Anna, could we go over how you created the graph with all the layers again, please?
The graph with all the layers, you mean that first plot that we did?
Yeah, it was the first one, yeah.
Yeah.
Thank you.
This one here?
Yeah.
Right, right. So this plot command is just your basic command for plotting like X versus Y, right? And you don't have to give it a label, that's optional. And so here, maybe I'll take this out for a second. So notice, you know, a lot of these, like, it makes the plot look nicer, but they're not necessary to make the plot. You know, what's going on here is plotting a vector, right? That's all. But this is just plotting vector Y. If you had 2 vectors you're plotting next to each other, you know, you would do X versus Y. So I could use this. This is my X values. So I could say X versus Y. I could plot that too. Here I get the same plot because these were just the indices to start with. The default is to kind of connect these with lines, but I make this into a scatter plot by adding this little O argument. And in that case, returns them as dots. And so that's really useful if you're like exploring correlation and you want to do X versus Y. You might change that to a little O.
Gotcha. So
is that helpful?
Yeah, thank you. So if I were to create a second graph, same graph, how does Python know where to add the layer? And I want it on the second graph, not the first.
So you want to do 2 graphs, not just one?
Uh-huh.
Yeah, so then you can, for example, just use this show command to tell it that you want a new figure. So basically, if you put this, it's going to be like, okay, show the current plot. Then it'll make a new one after that. So if I run this, it's going to make 2 of them, right? So this show command kind of separates into the different plots.
Thank you.
Yeah, no problem. Okay, why don't we go ahead and start the breakout rooms? And let's I know 10 minutes is not a long time, but we have a lot to go through today. So let's try for 10 minutes. And it's a short thing. So you want to go ahead and open this Jupyter Notebook 04 Descriptive Statistics activity. And let's take 10 minutes. So I'll end the breakout rooms in minutes. Let me see. Okay. So how many breakout rooms do we want to do? Is about 4 people good? Let's do that. Okay, I'll see you guys back in about 10 minutes. Have fun.
Anna, just to be sure, I'm not supposed to join a breakout room, right?
Oh, I think that's optional. I think you're welcome to if you want to, but you don't have to.
Oh, okay. I joined one and then I left because I thought they might want to do the activity on their own.
I know Alex, I think, joined one of the breakout rooms last time.
Oh.
So
I
I'm sure
think people can ask for your help, right? They can explicitly call on you to join a breakout room, and that's when I would do it.
Okay.
Oh, okay. I wasn't aware of that. So they're able to.
Yeah, they're able to ask.
How does that help for us?
What's it?
So how would that show up for us if we were like called to a breakout room?
You just get a message from Zoom, and
Okay.
then you can click the button and join that group.
Okay, I see. Okay, breakout rooms are about to get closed in 30 seconds. Looks like we have a lot of people back in.
Anna or Professor Little, I don't know what you want to call it, but is
You
this
can-
kind of an activity we can submit?
Yeah, you can submit it.
Should we just add like our name and user ID at the top, or just?
Oh, yeah, I'm sorry. I forgot to do that, didn't I? My bad.
No worries. Just making
I'm
sure that
sorry.
like it is something we can.
This was, yeah, first time that I did one, and I totally forgot to do that. My bad. So,
And what do you
yes.
prefer to be called? Sorry.
Oh, yeah, it doesn't matter. You can call me Dr. Little, I guess.
All right.
Okay, so let's keep going. So I am sorry about that. And yeah, so please add your name and your ID before you submit, as I forgot to do that. Okay, sorry about that. Okay, so in the last, I guess we've got 20, no, we've got 15 minutes. Okay, so we don't have a lot of time, but let's cover what we can. So one thing that we are going to be talking about later in this course is called inferential statistics. So far we've been talking about, you have a data set, and you want to compute some descriptive statistics like mean, standard deviation, but those things describe just that data set itself. What we're really interested in general is learning, by studying a data set, learning something about the underlying population that the data set was sampled from. But that's a more difficult question. You know, you can compute the mean of a data set exactly, but what is the mean in the population that the data set was sampled from? So inferential statistics gets at, well, let's try to learn not just about this specific data set, but what can we say, what can we infer about the population that the data set was sampled from? So for example, if you're dealing with election results, poll everybody, so you'll get some say, you poll some small, well, maybe a large group of people, but it's still not the whole population, and then you want to try to predict the outcome of the election from that data set. So we often model a population characteristic, right? Characteristic of the entire population as a probability distribution. And then inferential statistics is all about deducing properties of the underlying probability distribution from sampled data. Okay, so we'll talk about just a couple of famous distributions, which will come in handy later to know about them. So first of all, there's the Bernoulli distribution. And a Bernoulli distribution is pretty much the simplest distribution you can have. It's just a coin flip. So the Bernoulli distribution, named after Jacob Bernoulli, is the probability distribution of a random variable, which takes the value of 1 with probability p and 0 with probability 1 minus p. Okay, so it's like a coin toss, fair coin. You'd have probability 0.5 of success and probability 0.5 of failure. But in general, you could have any probability of success for Bernoulli. Okay, so this is just a coin toss. We can actually use Python to sample from a Bernoulli distribution. For this, you can import the SciPy package as SC. And specifically, if you want to import these specific distributions, you can import from SciPy stats, Bernoulli, binomial, normal, and that will be handy for these. Let me go ahead. Actually, I think I ran this whole thing, so I don't think I have to do this, but just in case. So for example, let's say I want to take a sample size of 1,000, and I want to simulate flipping a coin 1,000 times. So I can do Bernoulli.RVS. That's short for random variates. So I'm going to generate 1,000 random variates with a probability of success of 0.5 and a sample size of n. And I'll just print the result. And you can see I just made a long list here of coin flips. Okay, and if we want to see how many heads we got, we can just sum. We got 492. And if we want to know what percentage of head we can divide by the total number, and we see that's 49.2%. Okay, now we could make the sample size even larger. So we could, instead of doing 1,000 coin, let's do 1,000,000 coin flips. Let's really crank it up. What we would expect in that is that the percent is going to get closer to 50% because we're taking a larger sample size here. So if we increase this up to 1,000,000, we see we get 49.955% heads. Okay, so some basic facts to keep in mind about a Bernoulli. A Bernoulli has mean P and has variance P times 1 minus P. And what we saw here when we did the simulation, and when we simulated a Bernoulli in number of times, and then we added up a total number of successes that we got, this value itself, this 492, that actually is also a random variable, and it's called a binomial random variable. It has a binomial distribution. So a binomial distribution with parameters n and p is the total number of successes that you get when you do n independent Bernoulli random trials, each of them with success probability p. Okay, and so let's see. So for example, we could take p to be 0.5 again, and then we may not be interested in keeping track of individual flips. We just want to know overall how many we got, what that sum is. Let's simulate the binomial. So let's say again, we have a fair coin toss, probability of heads 0.5. And let's say we're going to toss the coin 10 times, and then we're going to see how many heads we got. So the possible values for the random variable here would be 0, 1, 2, 3, all the way up through 10. So I can use the binom.RVS to simulate these binomial random variates. I have to specify n, I have to specify p, and then I have to specify the sample size that I want. So here we're doing a very large sample size, so we're going to get a lot of observations of this. But you'll notice if I print them, each one is going to be between 0 and. Okay, let's see, did I miss a question?
I think I've responded.
Okay, great, thank you. Then I'll keep going, try to get to the end of this. Sorry, I'm speeding up a little bit.
Another question that you might want to take a look at. What the chance of a team winning a sports tournament be Bernoulli, since it only has 2 outcomes, win or lose? Or is it not, because a team winning might not be independent from other teams?
Okay, so that's a really good question. So would you think of this as a Bernoulli or not? Do you have independence here? It's actually rather uncommon in the real world to have true independence. You know, this is kind of a thing that we assume mathematically that often doesn't hold in the real world. Still, sometimes we would model things as if they were independent, and sometimes that still leads to useful results. So that's a hard question to answer precisely. You know, I think, yeah, in practice, no, they're not independent. But you could model, I think you could model a sports team's performance each game as a Bernoulli with a set success probability of basically how good the team is. Again, that model wouldn't be perfect because it would depend on what team they're playing. And then you could model their total performance of the season, like how many wins they get during the whole season as a binomial, counting them up. And yeah, I think those wouldn't be perfect models, but it would be a good first simple model to do. Good question. Okay, so here I've simulated my binomial, and then I could make a histogram if I want to see the values. So here, once again, I'm specifically defining what bends I want to use, then calling the hist function with those random variates that I generated and using the bends that I made. And here I'm adding something that I didn't have before, which is density equals true. What is that going to do? That's going to normalize the histogram. And so instead of displaying the total counts on the y-axis over here, it's going to divide by the total by the sample size of the data. And so it's basically going to approximate a function with an area of 1 under the curve. So this is a normalized histogram, which is going to sort of approximate what we'll discuss here in a second is the PDF function. Well, I guess a discrete variable doesn't have a PDF, but a continuous one does. And so here we see the histogram of the binomial. Okay, so a couple of fun facts. So the binomial has mean n times p and variance n times p times 1 minus p. So you might think that that's weird. Oh, why does the variance increase with n? Wouldn't it be better if you have a large sample size? But this is the total number of successes. If you divide and make that a percent, you'll see, indeed, yes, it decreases with n, and things get better as you increase the sample size, but you kind of have to compute the percentage. Okay, so one thing to keep in mind, so we started the class today talking about categorical and quantitative variables and how quantitative variables can either be discrete or continuous. Discrete random variables have their probabilities described by something called a probability mass function. So a discrete variable will take on a discrete set of values. For example, for the binomial, it's 0, 1 through n. And then if we really want to know everything about that distribution, we have to specify, well, what's the probability that you get a 0? What's the probability you get a 1? What's the probability you get an n? The probability of getting all of those values, and that's what the probability mass function does. And so here you can see the probability mass function for a Bernoulli and for a binomial. And here you can see that we can plot also the probability mass function. So there's a built-in, what we plotted before was just the histogram from the simulations, but there's a built-in Python function, binom.pmf, which will return the probability mass function values for a binomial defined with parameters n and p evaluated at k. Okay, and so if I make a plot of this, you'll see it's very similar to the histogram that I got from the simulations. And indeed, this histogram is an approximation of this this exact probability mass function. Okay, let me skip the concept check because we've talked about all that. And just briefly in the last couple of minutes, let me mention one of the most important distributions, probably the most important distribution in all of statistics, which is the Gaussian distribution, which I think you're probably familiar with. It's famous for being described as this bell-shaped curve. And this distribution is determined by two parameters that we've also already talked about, the mean mu and the standard deviation sigma. Okay, so whenever you're dealing with a normal distribution, you should make sure you know what the mean and the standard deviation are. So we can start off defining them defining mu and sigma. And then what we're doing here is we're just making a list of X values. So this is just a long list that basically takes values between the mean -4 standard deviations and the mean +4 standard deviations. And then if we pass this into the norm.pdf function, it's going to evaluate the probability density function vector. We have to specify what the mean and standard deviation for the distribution are, and you do that by the second and third arguments here. And then you can see if you plot those values evaluated at the corresponding PDF values, you get this nice bell shape. Okay, so what I'm plotting here is called the probability density function, or the PDF function, which is what you need to completely describe a continuous, the distribution of a continuous random variable. So for a continuous random variable, you can't list out every single possible value and write out a probability that goes with it. For a continuous random variable, we calculate the probability of being in between two values A and B by integrating the PDF function between those values A and B. Okay, so that's what's special about the PDF. You integrate it between two values to compute the probability of being in between those two values. And so here you can see that if I want to know the probability for this normal distribution of being in between -1 and 1, that's just going to correspond to the area under the curve in between those values. And you'll probably, I'm sure you've learned about the fundamental theorem of calculus when you took calculus, and that's actually related to the what's called the cumulative distribution function, which is frequently used to compute these probabilities. So you can think of the cumulative distribution function as an antiderivative of the PDF, of the probability density function. And so you can actually explicitly compute the probability of being in between A and B, if you know the CDF, by evaluating f of B minus f of A. So that gives you kind of a nice way to compute probabilities without actually having to evaluate integrals if you would rather not evaluate those integrals. And Python has these CDF function values. So there's a norm.cdf, which you can use for computing probabilities. So for example, here, if you do the CDF function evaluated at the mean +1 standard deviation minus the CDF evaluated at the mean minus the standard deviation, you can see there's a probability of 0.68 of being in that range of the data. Okay, so I think, sorry I sped up so much there at the end. I was worried this was going to be too much content to cover in one lecture, and I think it was a little bit ambitious, but I think we got through the important things. So, so let's kind of wrap up there for the day, and let me know if you have any questions. Are there any questions before we close? Okay, so we have a question. Do we submit the task to activity 2? Yeah, so let me double check on that. So I may not have posted on Canvas where you need to submit that yet. So let me make an announcement right after class. Any other questions? Okay, thanks everybody, and see you, see you next time. Have a good one.
I actually wanted to ask a question about the last activity.
Yes.
Because I was in class and I submitted it, but I didn't know that there was nowhere where it indicated that there was a due date by 8. So I submitted it after, not knowing. So I just wanted to make sure that there's a way for me to get those points still, even though, because I didn't know, it didn't say anywhere that it had to be by 8, and it wasn't until he put it in the Slack channel that I saw it.
Oh, so you mean the activity for today, or you mean
from
the
the last lecture?
Oh, the activity from the last lecture, you weren't aware that it was due by 8.
Yeah,
and
so I was there and I did it and I turned it in at 9:50 thinking I had to finish it and submit it. But then in the Slack, he says that it's not, we don't have to finish it. We just have to submit it before 8. But
yeah, so the activities, they're more, based on like completion, that like, did you do a good faith attempt at it? So they're not rigorously graded. I would think that if you weren't aware of the 8 p.m. submission, I would think the 9:50 would be okay the first time, but then moving forward.
I just didn't know
forward,
because there wasn't anywhere that it indicated it, and I was just so
yeah, moving forward, then it would be probably more strict, but I think that's fine for this time.
Oh, okay. And then so this is just activity 3 that we submit these exercises to.
Yeah, so I did not like, I think I didn't post on Canvas, but yes, I think that should be.
All right, thank you so much. I appreciate it.
Yeah, no problem. You too.